Welcome back to the Deep Dive. Today we're jumping into something really fascinating from the online encyclopedia of integer sequences.
The OEIS, yes, always a source of gems.
Absolutely. We're looking at sequence A000339. Now the title is Number of Partitions into Non-Integral Powers.
That definitely catches the ear, doesn't it? Non-integral powers.
It does. It sounds almost contradictory. How do you partition using something, well, not whole? Our mission today is really to unpack that. What does it mean? Where did it come from? And what's it telling us?
Exactly, and it's a bit different from your standard integer partition problem. Usually you're summing integers. Here, the idea involves, well, powers that aren't integers, specifically square roots.
Square roots, okay.
So understanding the precise definition is really the first step. It's the key to the whole thing.
Right, so let's get precise. How is A000339 formally defined? What are we actually counting?
Okay, so R.J. Mathar provided a really clear comment on this back in, I think, 2009. He defined AN as the number of solutions to an inequality.
An inequality, okay.
Yes, it's on by 1 to the power of 1/2 plus by 2 to the power of 1/2 is less than or equal to n.
So square root of by 1 plus square root of by 2 is less than or equal to n.
Precisely, and there are conditions on by 1 and by 2. They have to be positive integers. And crucially, by 1 must be less than or equal to by 2. So 1 by 1 equals by 2.
Okay, that ordering by 1 and by 2 is important.
Very. It avoids double counting pairs like 1, 4, and 4, 1, for instance. So we're essentially counting ordered pairs by 1 by 2 whose square roots sum up to n or less. That's the connection to non-integral powers.
Got it. Let's make that really concrete. The sequence starts after an offset 1, 5, 18, 45, 100.
Right.
What about that first term, A2, 1? How does that work with the inequality?
Okay, good example. For n2, we need solutions to squared I1 plus squared I2 with 1 plus by 1 by 2.
Right.
Well, let's try it. 1 by 2 is 2.
Which means squared by 2 equals 1.
Exactly. And since by 2 has to be an integer, that forces by 2 to be 1. So by 2 must be 1. And since we need by 1 equals by 2, the only possible pair is 1, 1.
Just one pair.
Yeah.
1, 1.
Just the one. And that's why A2 is 1. It's quite neat, isn't it?
It is. It shows how the constraints limit things, especially at the start. But then A3 is 5. It jumps up.
It does. As n increases, the possible values for I1 and by 2 expand, and you get combinations like 01, 1, 1, 1, 3, 1, 4, and 2, 2, satisfying the inequality for n3. Suddenly, many more pairs work. It shows that complexity we often see in number theory arising from simple rules.
So who first looked into this sequence? Given its unusual definition, does it have a long history?
Oh, it has quite a distinguished history, actually. The author listed in the OEIS is N.J.A. Sloan himself.
The founder of the OEIS. Wow.
The very same. And it wasn't a recent addition. It was already included in his Handbook of Integer Sequences back in 1973.
73, so it's been around for a while.
And then again in the Encyclopedia of Integer Sequences in 95. So yes, it's a well-established sequence.
That's really interesting. Given that history and a slightly odd definition, does it connect to anything outside of, pure number theory?
Yeah.
Any unexpected applications?
This is where it gets particularly fascinating, I think. The OEIS entry points to work by Agarwala and Alluk from 1951.
1951. Even earlier.
Yes. Their paper was titled Statistical Mechanics and Partitions into Non-Integral Powers of Integers.
Statistical mechanics?
Yeah.
Seriously. How does this sequence relate to physics?
It's quite remarkable. The idea, it seems, is that this mathematical structure, counting solutions based on sums of square roots, could potentially model certain physical systems. Perhaps systems where energy levels or other quantities aren't constrained to be simple integers.
Like energy distribution in some complex system.
Potentially, yes. It highlights how these abstract counting problems in number theory can suddenly provide, well, a language or a framework for thinking about phenomena in completely different scientific fields. It's a beautiful, unexpected link.
That really is an aha moment. And exploring these connections, or even just calculating more terms of the sequence, must require some serious computing power, right? I see mentions of Maple and Mathematica code.
Absolutely. R.J. Mathar and Jean-François Alcover provided code examples. For sequences like this, especially when you want to see the long-term behavior or check for patterns, computation is essential. You simply can't generate thousands of terms by hand.
These tools let you see things you otherwise wouldn't.
They really do. They help uncover the deeper structure, maybe asymptotic formulas, or just verify conjectures. It's a vital part of modern number theory research.
So bringing it back to students listening in, why is A000339 a good sequence to maybe spend some time with?
Well, I think it's a great example because it starts with a definition that looks maybe a little strange non-integral powers, this inequality, but then you see it leads to a concrete counting problem.
Right, with integers by 1 by 2.
Exactly, and then it connects outwards, it has history, it links to physics, it sort of encapsulates how a specific mathematical question can be richer and more connected than it first appears. It encourages that broader way of thinking about number theory.
Okay, so to wrap up, we started with this intriguing name, partitions into non-integral powers. We found it means counting integer pairs by 1 by 2, satisfying sqrt by 1 plus sqrt by 2 equals n. We saw the first few terms, touched on its history with Sloan, and found this surprising link to statistical mechanics.
It's quite a journey for one sequence.
It really is. So what's a final thought for our listeners to take away from this?
I suppose it's this. A000339 connects number theory to statistical mechanics. It makes you wonder, doesn't it? How many other sequences in the OEIS, maybe hundreds or thousands of them, hold similar keys? Keys that unlock unexpected connections between pure mathematics and, well, the structure of the universe or other scientific fields. What other bridges are just waiting there in the data yet to be discovered?
A great question to ponder. It really speaks to the power and the ongoing adventure of exploring resources like the OEIS.
Absolutely. The exploration continues.
Indeed. Well, thank you for joining us on this deep dive. We hope you found it interesting, and maybe it inspires you to explore the OEIS yourself. Until next time, keep exploring.